Good morning or afternoon, everybody. I thought I had 30 minutes. Turns out I have 20, so I'm going to go kind of fast. I thought I had 20, now I have 18 minutes. All right, so this is a login traffic for one of our customers. This is what the traffic looked like prior to the application of any client-side signals. And I'm going to go into detail what I mean by client-side signals in a minute. There are a couple of things that were alarming about this traffic. The first thing is the lack of a day-night pattern. When you're looking at what should be human traffic and it doesn't have that day-night pattern, that's a cause for concern. We're normally logging into our accounts while we're awake, during the day, not so much at 2 o'clock in the morning. Another thing that concerned us was that no matter what our customer did from a marketing perspective, email, blast, television commercials had no effect on this traffic whatsoever. So they had no idea if their marketing dollars were well spent. The other thing is the volume and velocity. 2.5 million attempted logins per hour, that's too high. This customer has millions of customers, but they shouldn't be logging in at that velocity. All right, so now, prior to the application of signals, I'm going to talk to you about what I mean by signals. This is a replay of the user's interaction with this login form. At the top there's a timeline left to right. Each of those tick marks corresponds to an event that's played out at the bottom. In the far left, you're going to see key events, key down, key up events. You're going to see mouse movements, mouse clicks, more key down, key up events. We take all this information, we apply some algorithms to it, and we generate various types of user fingerprints. This is an example of an automated interaction. You're going to see key events on the far left that are too fast to be human, and then mouse clicks on different areas of the screen without any mouse movements. We call that the magic mouse. You cannot do that. It can only be done synthetically. Here's a woman entering in her password 3 separate times. They may not look identical, but if you break it into sections, it's identical. And think about it, this makes sense. Over time, as you type in your password over and over and over again, you develop a rhythm when you enter in that password. This is how a bad actor enters in the same password. It's certainly possible for a bad actor to get the password off the dark web or through a compromise, but the bad actor is not going to be able to match the rhythm of the victim typing in the password. This is probably the best illustration of the difference between humans and bots. On the left, in green, you have mouse movements and red mouse clicks. It's hard to see, but there are mouse clicks here. There's no event listener there, but we click areas on the screen where nothing happens. When I first saw this, I thought maybe it was erroneous data, but then I started paying attention to my own habits and watching my friends and family and loved ones, and we do. We occasionally will click areas on the screen where there's no event listener. I don't know why, but we do. You look over here, you can see the size, shape, and position of the submit button based exclusively on where the bots click. They have no incentive to click anywhere but the submit button. Look at mouse movements. Think about how we move our mouse. We don't just move it to a submit button. Sometimes we do this to wake it up, to find the mouse. Sometimes we use it to track where we're reading. Over here, the bots, they don't do that. They move the mouse either in perfectly straight lines or even when they add entropy to this, smooth arcs and curves. Really the way these attackers, they generate enough entropy as they replay a human interaction. And it's the replaying that gets them caught. Now, if we look at this kind of left to right at speed of navigating a workflow, we see that the manual fraudsters are more efficient than the customers. They're less efficient than bots. Let me explain what I mean by that. If each of you were to pull up your phone and launch the banking app and then go to log in and then add a payee and then send that payee money, my guess is you'd have to look for the add payee button. Not for very long if it's a good user experience, but you'd have to look. You don't add a payee every day. Bad actors add hundreds of payees per day. So they navigate that workflow lightning fast. So when F5, we first go into mitigation mode, get rid of all the bad bots, we list all the good bots, then we look at the humans and go, who's navigating workflows lightning fast? Because they require a second look. In addition to behavioral biometrics, we also interrogate the browser, collect things like plugins, font, screen size. We take all this information, apply some algorithms to it, and generate what we call a browser fingerprint. The real power at F5, though, is in our additional signals. So let me give you a preview of a couple of those. This is what we call our emoji signal. It leverages the fact that different platforms render emojis differently. So if the user agent string purports to be Chrome, but they're rendering emojis like Firefox, we know they're lying about the user agent. And your legitimate customers have no incentive to lie about their user agent. Some of you might recognize this top string preceded by 0x as a hexadecimal number. Hexadecimal has 0 through 9 and A through F as a number. It's a very large number. We'll ask the browser to convert it into decimal, and you see we get a number on the order of 18 quintillion. You'll also notice that different browsers get a different answer to that large floating point math problem. So just like the emoji signal, if they're purporting to be Edge, but they're doing floating point math like Chrome, we know they're lying. So this is 2 of our special signals. We have dozens of them that we don't talk about them. We don't file for patents on them because they're virtually impossible for bad actors to spoof. Also, the HTTP header, we apply some algorithms to that and generate what we call a header fingerprint. The powerful thing about this fingerprint is that we collect it whether or not our JavaScript executes. And we've tracked many attackers using just header fingerprints. All right, we go back to the login traffic. We apply the signals to see virtually all of it is attack traffic. This was jaw-dropping for the customers, you might imagine. The quote on the screen is from the CISO. And this is very common. It's very, very common for organizations to underestimate the size of the problem. And the reason is these attacks are coming from tens of thousands, hundreds of thousands, and even millions of IP addresses. And these security teams are typically pretty good at identifying the top few hundred noisiest IPs, but they miss the long tail of IPs, hundreds of thousands of IPs, where there are very few transactions coming from each. And they do this because for years they've been mitigated by IP. Years of playing whack-a-mole has forced them to become highly, highly distributed. And there's the day-night pattern along the bottom we were looking for. And no wonder marketing didn't know if their dollars were well spent. That's the traffic it was influencing. So it was dwarfed by all the attack traffic. And think just for a moment of the consequences of this much attack traffic. It isn't just about account takeover and fraud. Think about latency at origin. Think about performance. Think about costs associated with CDNs and fraud tools. Anything that charges per transaction. Enormous costs. So at F5, we went into mitigation mode. Okay, everything in yellow, we're flagging and passing to origin. We go into partial mitigation mode, full mitigation mode, and then something very important happens here. And there are 2 things that if you learn nothing else, 2 things. You must have client-side signals, and you must have a second stage of defense. And let me explain to you what I mean by that. So we have JavaScript that runs inside web and mobile browsers, collecting some of those signals. We also have an SDK that sits alongside native apps for the purpose of collecting signals to identify spoofing, to identify bad actors. All those signals are sent through the internet to an appliance. The appliance looks at those signals and makes a real-time determination if the traffic is good or bad. If it's good, it passes it to origin. If it's bad, it takes some sort of mitigating action. Well, look, there's something missing there, right? No red line, but that's a pipe dream. In reality, there will occasionally be bad traffic reaching origin. Attackers retool, new tools emerge. You have to have a second stage. This is where your AI and ML systems are running, and I'm surprised. Thank you for, none of you rolled your eyes when I said AI and ML, because often I roll my eyes when people say AI and ML. If I could squeeze in blockchain, it would be the trifecta. But we're quite good at it at F5. F5 acquired a company called Shape Security about 2.5 years ago, and Shape Security was in the top 100 in the world according to Fortune. Very effective, and F5 continues to invest tens of millions of dollars in it. Even though we're good at it, we recognize it is not ready to be blindly trusted making decisions about whether or not to mitigate one of your customers. It isn't. You must have humans poring over all those alerts, looking for false positives, and it isn't enough to find something in stage 2. You need the ability to update stage 1 to deal with the newly found threat, okay? And this is what F5 offers into perpetuity. Real-time defense in stage 1, human-supported AIML in stage 2, looking at aggregate transactions, looking for what we may have missed. And then updating stage 1. A common question is, how often do you have to update stage 1? We might do it 4 or 5 times in a day if we're dealing with a particularly aggressive attacker. Other times it might be a few times, every few days, or maybe once a week. Our customer does not have to be under attack for us to update stage 1. We might see an attack somewhere else across the network and want to proactively protect our customer from that attack. That will also cause an update. And this sort of multi-stage defense provides remarkable efficacy. I've got hundreds of these before and after where you go online, there's a lot of unwanted traffic. We go into mitigation mode, do battle with that attacker, and then over time, all of our steady state customers enjoy less than 1% unwanted traffic reaching origin. All right, so we detected the retool in stage 2. We pushed out a countermeasure in observation mode, not taking any mitigating action on it. This is what allows us to know when we go into mitigation mode, we're not going to impact any legitimate customers. No false positives, because we're in observation mode here. We go into a mitigation mode on that countermeasure, and this attacker moves on to a different target. This is very typical, the type of engagement F5 has with various bots. So why are they doing this? This is credential stuffing, where bad actors taking hundreds of millions, sometimes even billions, username password pairs, and trying them programmatically against the login page of everyone else. And because of consumer habits to reuse usernames and passwords across websites, we end up taking over 0.1 to 3%, that's the takeaway, 0.1 to 3%. When you're trying hundreds of millions, you compromise a lot of accounts. It isn't just login though. Here's create account traffic. Everything in yellow is automated. Automated attempts to create bots, to create accounts. You really have to zoom in to see the organic human traffic. Imagine waking up one day to find out you have hundreds of millions of synthetic accounts on your network. This is add to cart prior to the application of F5 signals. Obviously, no day-night pattern. I mean, there's something wrong with this. We apply the signals, you see virtually all of it is automated. This isn't even our record. We've seen 99.9% of all traffic hitting various applications as being automated. Why? Limited time offer sales on add to cart. They really want those sneakers and they sell them on the secondary market for significant profit. We've done studies on some organizations, they're making millions of dollars by doing this. We have to take away all the automated traffic to see the day-night pattern of the human traffic and the occasional spikes for the loyal customers really trying to go after those products. These are all the public-facing applications that we see vast amounts of automation on. We see the fares for hotels and airlines scraped constantly. Sometimes that results in locking up their inventory. When you pick the city and the night and the room, suddenly that room's held for 15 minutes. When a third party or competitor is scraping all of that, it locks up the entire inventory for 15 minutes. Seat mapper, we see, for some reason, 500 times the human traffic hitting the seat mapper endpoint. I talked about create account, add to cart, login, fare search, hotel search, find a doctor. I'm not interested in it, but there are some third parties that want to know at an insurance company, every doctor in their network, what their specialty is, what their contact information is, where they went to school, and the way they do that is by using automation on the find a doctor endpoint. All of these things, we see vast amounts of automation. And we call, our capability to stop unwanted automation is called bot defense. And our booth is right over there after the presentation. I'll be over there to answer any questions you might have. So after, people often ask, they go, look, you inject JavaScript, you must introduce some latency. And that's true, you cannot execute JavaScript without taking some time. But we typically see a net improvement in performance because when you get rid of vast amounts of automated traffic, then origin typically improves in performance. So these spikes correspond to attacks. And once we go into mitigation mode, the origin latency goes way, way down. All right, what else can you do with client-side signals? Yeah, you could find bad actors, of course, automation. I talked about speed of navigating workflow, typically indicative of a bad human, a human doing some bad things. Pasting operations is another way. Bad actors, they paste a lot into fields that you would not ordinarily paste. So that's a common signal. Screen utilization. Good customers normally take up the whole screen with the browser. Bad actors, they'll maybe have a lower screen utilization because they have a terminal window open or a spreadsheet or something else that's helping them further their activity. Log out. I know we all want our customers to log out all the time, but they don't. They often just close the tab or close the browser, turn off the machine. Bad actors log out all the time. That's something you could put to use right away. Go back, bad actors log out all the time. They have to because they have to log into the next account. So the way they work is they'll do everything they can to change their fingerprints, their environment. They'll log in, they'll log out, they'll do everything they can to change their environment, then they log in and they log out, but they always log out. Talked about emoji signal and floating point math. We'll look at the time zone of the IP address compared to the time setting, the time zone of the browser, indicative of VPN usage. This focus switching is Alt-Tab on a Windows machine. Bad actors, they they switch focus a lot as they go back and forth between applications. And then finally, a lot of our signals can be used for a very powerful device ID. We see them trying to change the way their device looks, but we know it's the same device. And when we see that same device attempting to log into more than 3, 4, 5 accounts, I mean, think about it. How many accounts at an organization do you log into? Maybe yours, your partners, maybe kids, but if you start trying to log into 10, that's anomalous. Network intelligence is probably the most powerful. If we see a device somewhere across the F5 network engaged in malicious activity, and now we see that device on your site, chances are that's also malicious activity. So network intelligence is very powerful. So we call this account protection, where we analyze all those signals, and in real time, we will make a recommendation right in the HTTP header, and then at origin, you could take steps on it. If it's firing off all sorts of alerts, we tell you, look, we're positive, this is malicious, don't let any money leave the organization. Or maybe it's just checking a few boxes, and maybe you just issue an MFA challenge. All right, so here's an example of some manual fraud. This is a click farm using fulls from the dark web to apply for credit in somebody else's name. We looked at the key events, and we saw 2 key down and two key up events. Our signals told us this was a pasting operation, but it was in first and last name. I've never pasted my first and last name. I've gotten pretty good at typing my name over the years. And this isn't autocomplete. This is them hitting Control and V for the first and last name. Very alarming. The second issue was mouse movements and mouse clicks. Not a lot can be gleaned just by looking at this, but if you overlay the protected form, from one application to the next, to the next, to the next, the mouse never leaves the submit button. That's unusual. Normally what happens is you see somebody, a bad actor will use a keyboard to navigate the entire application, Alt-Tab, Control-C, Control-V, because that's fast. And then he or she will reach over and touch the left mouse button that is sitting over the submit button from the previous application. Very unusual. This is what most of the legitimate applications did. Mouse would move to the first name text box, they click it to give it the focus, they type their name using key down, key up, and there were no pasting operations. Okay, so those are some of the differences between the fraudulent applications and the legitimate applications. Here's another one, strange clustering. Each of these is a user fingerprint, so all the mouse movements, keystrokes, and everything associated with one completed application through their browser, through their autonomous system number. Think of that as the organization from which you get your IP address. This is what we expected, but instead we see this. Lots of applications being submitted through one browser fingerprint and one autonomous system. Now this by itself isn't necessarily alarming. When you all flew here today, walked through the airport, you saw probably a kiosk that says, apply for a credit card here and you get 40,000 frequent flyer miles. That would result in this sort of pattern. So one of these signals isn't just the slam dunk, it's bad. It's always the totality of the signals. Here's the final anomaly. 00 for the screen, there's 00 for the browser. There was a strange 300 pixel shift right there. And this goes to the screen utilization score I was talking about. We also noticed the screen move off the left side, the mouse would move off the left side of the screen, come back, pasting operation, off the left side of the screen, come back, pasting operation. So we suspected that's where the fulls were being kept to complete the application. So we took all this, we identified it in stage 2, and then we pushed an update to flag all future applications that shared these attributes. And we're flagging roughly 1,000 applications per day, saving millions. All right, so what else can you do with signals? We've talked about stopping bad automation, and we've talked about stopping bad humans. This is now improving user experience for your good customers. This is actual data for one of our customers. We noticed roughly 20% were struggling to log in. And we believe there's some percentage of them that's going to cause customer service. It represents about 2,000 calls per day, a significant cost associated with 2,000 calls per day. Well, we studied those signals very carefully, and we said, look, 6,800 of these and 1,100 of these are known good. We're positive they're your customer. Your customer, they're using their device, rendering emojis like they always have, doing floating point math like they always have. There's no reason to ask them to enter their username and password again. So they used it to do a session extension. And we call this authentication intelligence, using these client-side signals to do silent authentication, imposing no friction on the customer. And this is from our customer. This is not one of our charts. They did A/B testing. Here is a 7-day session timeout versus a 30-minute session timeout. That's it, just changing the session timeout based on the client-side signals resulted in a measurable uplift in revenue. Huge success. All right, we're down to 28 seconds over. Here are the takeaways. One thing I didn't say is, that I want to emphasize is you have to harden your SDK and your JavaScript. You start collecting these sorts of signals, bad actors are going to reverse engineer it and try to spoof those signals. So it's really important that you harden your JS and SDK. All right, so I'm out of time. Our booth is right over there. I'm going to go over there, and if you have any questions, I'd be happy to answer them over there. Thank you.